The goal of this project was to create a monochromator using a smartphone and 3D printing. A monochromator is a device that takes in polychromatic light, such as white light from the sun, and produces only monochromatic light, or single-colored light, at the exit slit. Commercial monochromators are quite complicated, using mirrors and lenses in order to culminate light and create an intense, powerful output of light. However, a much simpler monochromator can be used. A monochromator works on one basic property of light, diffraction, and by extension dispersion. The most common example of diffraction is a prism creating a rainbow from sunlight or another source of white light, such as seen in the picture. Diffraction is the bending of light as it passes through a narrow slit or across the edge of two mediums. Light of different wavelengths experience diffraction more or less strongly, which leads to dispersion. This dispersion is the reason why white light, or light that contains the entire visible light spectrum, creates a rainbow color after passing through a prism. In the early design phase for this project, we decided to use a prism in order to diffract our light. However, after obtaining a prism and doing some simple tests with it, we found that the results produced by the prism weren't doing too well, and the light wasn't dispersed enough and wasn't intense enough. So instead, we decided to use a diffraction grating. A diffraction grating uses diffraction by using a bunch of tiny slits that are spaced very close to each other. In our case, we used a diffraction grating with 1,000 lines per millimeter. The final design of our project was this. In the center, you can see the main body of the monochromator. In the front side of it, you can see the mount for the smartphone, with a hole cut out for the camera lens. On the left, you see the top lid, and on the right, you can see the front spacer with slits in it at various lengths. We decided to do multiple slits instead of just one in order to reduce the amount of 3D printing we would have to do. These are the parts after 3D printing. We have the body, lid, slits, a diffraction grating, and black electrical tape, which was used for preventing light leakage. First, the diffraction grating was placed onto the slit and secured with tape. The slit then goes into the body, and the top lid goes on to keep everything in place. Black tape was then used on the edges for light sealing. To gather our data, the monochromator was placed on a rotating platform and was first angled at the sun. Then, the platform was rotated, and in increments of 4 degrees, starting at 25 degrees, we took pictures. Here are those pictures, starting at 25 and incrementing every 4 degrees. On the lower portion of the screen, you can see the expected values for these degrees, and the associated nanometers for the wavelength of the light. The first 3 are very similar, and the last 2 aren't quite as similar, but are still fairly close, and are in the ballpark of what we were looking for. Here's a video of the monochromator being slowly rotated. As you can see, overall, we were fairly satisfied with our results. We felt that the 3D printing was successful, and that the real versus the expected color were very similar. As for improvements if we were to do this again, we would come up with a more robust method for turning and measuring the grating. Also, it would be nice to discover a computational method for obtaining wavelength from a picture. However, after doing copious amounts of research, we determined that it was not possible to do this, unfortunately. Also, we'd like to have tighter tolerances while printing. Some of the parts were a little loose or a little too tight, and this is partially due to using multiple printers. So in the future, we would like to use just one printer to make sure that the device is as accurate as possible.